kinetics. And so I just want you to be able to recognize two common nonlinear patterns that you see. And so if we have a linear, if this would be linear, that is, if we're measuring the concentration of the reactant, and the reactant is being consumed at a constant rate, like this, then we have to just collect enough data to define this line, the linear line, and then we have a mathematical equation that can allow us to do any kind of predictions we need to. That is just y equals mx plus b, where y is the concentration at any time t, m is the slope. The slope is the delta A over delta t. X is the time, and B is the initial concentration. And so, do we have to continually, let's say it's a very slow reaction, we don't have to necessarily wait until the concentration gets down to zero. As long as we have enough data to define this as linear, we can predict how long it will take the concentration to get down to zero at time t by using this simple equation. Or, we can predict the concentration at any time t. And so this is a linear. Okay, but when we have nonlinear, then there are, different shapes to this, but there are only two shapes that you're going to worry about. The first shape is called first order. And to figure out what that shape looks like, we take the initial here and then cut it in half. When we cut the initial in half, it takes a certain amount of time, which we call T1 half, the time it takes for half of the original amount to be consumed. So we get that. And so now it looks linear, right? But how many data points do we need to define a line? At least three, right. To define a linear line, you only need two, but we don't know if it's linear or not, and so we need a third data point. Now, for the third data point here, if we cut this amount in half, then it turns out that it takes the same amount of time. This would be T1 half. That is, each time we cut the concentration in half, it takes the exact same amount of time. And so what we say is T1 half is constant. It's equal. And so at the next T1 half interval here, which would be the total of three T1 halves, or three half-lives, we should be down to here in terms of concentration. And so here it's going to be 1/2 the initial. Here we'll have 1/4 the initial. Here we'll have half of that, which would be 1/8 the initial. And so in 1, 2, 3 half-lives, we're down to 1/8 initial. And so if we have a curve like this, we don't want to wait until the concentration gets down to zero, because how long would it take for this concentration to go down to zero? How long would it take to completely consume all my reactant? Infinite amount of time. So there's no way we're going to do that. And so we're just going to get 3 data points to define this. And hopefully the 3 data points are spread out. Because sometimes if the 3 data points are clustered, let's say right at the beginning, it's hard to tell. Is that linear or is that a curve? When you spread them out, then you're going to get less error associated with that. All right, that's first order. And interestingly, what happens with the rate, the rate is the slope of this. And so let's take a look at the rate. The rate starts out quick, or initially here, and then it starts to slow down here, here, here. And so when we look at the rate, at time 0, we would draw the tangent here, say, and we get the slope. And so the rate is equal to the negative of the slope. When we get to time t1 half, the rate slowed down. And so here, this would be our initial rate, and this would be 1/2 the initial rate, and this would be 1/4 the initial rate, or 1/4 the slope. So we'll see this pattern here. All right, the last pattern you should look for, or at least try to familiarize yourself with, is going to look like this. It's also nonlinear, and it would be second order. Second order, we'll have a decay like this. We'll start off with an initial amount of reactant here, and then we'll consume half of it. We'll call this T1 half. It'll be about here. Okay, now this is our new starting point. If we consume half of this, we're down to 1/4, but the amount of time, the time interval will double. So this would be T1 half for the second period, which is, I'll call this initial, which is twice T1 half initial. It goes out here. Then I look at the next T1 half, cut this in half, and it would be double the previous one, or quadruple the initial. And so it's going to be way out here. Sorry. And so this would be the next interval. And so each successive half-life doubles, so it just expands out the curve. And so when we're looking at the slope here, we look at the initial rate, or the initial slope, and so we get rate 1 here. And then the rate here at the first one is actually 1/4 of the rate of 1. And at this one here, this would be 1, let's see, 1/4, this would be 1/16. So if the concentration, let me just think about it. The concentration doubles here, the rate increases twofold. So this should be, I'm sorry, this I think should be 1/8. Of rate 1. And so the other way of thinking about this is going in the opposite direction. So if we double the concentration, the rate should increase 4-fold. If we double the concentration, the rate should increase 4-fold, which means, I'm sorry, this should be 16. Yeah, 4/16. All right, so that's how the rate changes in this particular one, and this is how the concentration changes in this particular one. And so what we want to do is we want to come up with the definition of the line here. Preferably a mathematical definition, because that would be the most concise definition of this. And that way we can predict, what's the concentration at any time? How long does it take for the concentration to get to a certain or specified level? And the same thing here. We want the equation for this curve. And so we'll talk about that next time. So you just want to be able to recognize these for right now. These are two common patterns that we'll see.